It is my pleasure to introduce Trey Grainger, who is going to say things that are probably much better planned than what I've been saying.
All right, I think we're good. We'll go with it. All right, good morning, everybody. I am here today to talk about personalizing search using multimodal latent behavioral embeddings. You can shorten that to just personalized search. It's a little bit of a, I don't know what the right terminology is, but it's an area of search that everybody kind of knows about, but that doesn't get a lot of attention because it's weird. We know about running keyword search, lexical search. We know about dense vector search with embeddings and semantic search and all these different topics. Some are more in vogue right now, but personalized search I think is a very interesting area of information retrieval, and I just want to talk a little bit about it today, some techniques for implementing it, and then hopefully at the end we should have some time for questions and some general discussion around it. But I want to share some techniques that you guys might find interesting as you're implementing, whether it's a RAG system, whether it's a traditional, keyword-based system, semantic, vector-based system, what have you. So off we go. A little bit about me. I am the founder of Search Kernel, which is a AI-powered search consulting company. Also the lead author on the AI-powered search book. I'll talk a little bit more about that with Doug, who presented yesterday. I think everybody knows Doug. Formerly, I was the CTO at Presearch, which is a decentralized web search engine. And before that, I was the Chief Algorithms Officer at LucidWorks, and before that, the SVP of Engineering at LucidWorks. And before that, I was at CareerBuilder. The AI-powered search book, quick plug for it. It's coming out in about 2 months. It is finished. We're going through the production process with Manning right now. Two other plugs for everybody here, given the level of intellectual capital we have at this conference related to search and information retrieval. One, we have reworked the book in recent months to make it search engine agnostic. What I mean by that is it can't work with any database, but for most of the major vendors, the ones at this conference, the book was originally written to use Apache Solr. It still uses Solr by default, but all of the examples work in an sort of slightly abstracted way away from the core engine. So if any, and we've got an appendix at the back of the book for supported search engines and vector databases. So if anyone who I have not already spoken to is interested in potentially integrating with the book, so that the book will work with your technology and you can use the book to promote your technology, etc., definitely reach out to me either at the conference or afterwards. So just a quick plug there. Also, as we get ready to launch the book, I know many of you have read it. Many of you have early access copies. If you're interested in providing a quote about your thoughts on the book, hopefully positive, or a review, or anything like that in terms of helping us promote it, I would definitely love to chat with you as well. That'd definitely be greatly appreciated. The book covers topics from retrieval augmented generation, generative search and summarization, learning to rank, semantic search, dense vector search, fine-tuning LLMs in search, automated learning to rank, going all the way from building a learning to rank model by hand using manual judgments to generating automated judgments from in-click models from implicit user feedback and signals to active learning and exploration of other things. It includes sort of what you would expect in terms of the latest in terms of leveraging transformers and LLMs and doing multimodal search and those kinds of things. It also includes typical reflected intelligence type approaches like signals boosting, recommendations and collaborative filtering, and the personalized search I'm going to talk about today. It's not designed to be a latest and greatest model type book. It's designed to be the sort of design patterns for implementing search in a data-driven, machine learning-based way. So it's not going to be an evergreen book because our space is changing incredibly fast, but hopefully for years to come it will be sort of best practices for end-to-end implementing AI-powered search. So quick plug, there's a discount code, get it if you're interested, and off we go to personalized search. So the agenda for today, I'm going to talk a little bit about the personalization spectrum between search and recommendations, how to leverage user signals, their behaviors and interactions to implement collaborative filtering and personalization from latent features. use embedding vectors to generate personalization profiles of users, mix user signals and content-based attributes to generate multimodal personalization, clustering products and by embeddings to create personalization guardrails, context basically for the personalization, and then finally avoiding some of the pitfalls of personalized search. So before we get into all of that, I want to start with it seems like kind of a dumb question, but it's actually a really hard question, believe it or not. My question is, what is an embedding? And this is for actual, I want some audience participation here. So who thinks they've got a good definition of what an embedding is? Yep. Audrey, oh, so go ahead.
Numerical representation of one or more sets of pieces of data.
A numerical representation of one or more pieces of data. So like 12, maybe 42. Okay. Is that Audrey?
Me?
Yeah. Do you have something?
I was going to say, I guess, an AI representation of data that has magnitude and direction, and
Okay.
contains latent semantic information about the thing.
Okay. Let me get one more. Yep.
Yeah, similarly, a vector representation of a series of features that you can compare distance angle between that are represented in space so you can see how far apart they are.
Interesting. Okay. So we all could look at an embedding and say, hey, that's an embedding, right? So when we talk about embeddings, or I like the terminology thought vectors, though that doesn't seem to have caught on. We've got like word and phrase embeddings, sentence embeddings, paragraph embeddings, document embeddings. And so what I figured I would do is go to the experts in terms of, what does the word embedding mean? And by the experts, I mean what results come up on the first page of, Google or DuckDuckGo as search results. And then from those, filter out random blog posts and focus on like companies that should be able to define this, right? So I picked a few examples. One's from Hugging Face, that they seem like they would be legit, right? Their definition of an embedding is a numerical representation of a piece of information. Pretty good. Cloudflare, I don't know why they show up at the top, but they help. I think they have, I don't know. For whatever reason, embeddings are vectors created by machine learning models for the purpose of capturing meaningful data about each object. So by their definition, if I make my own embedding, if I put a vector together of features, that's not an embedding, I guess, because it wasn't created by a machine learning model. Hugging Faces, if it's not a numerical representation, it's not an embedding. Well, that's interesting. We'll come back to that. Google, theirs is very confusing. This is from a training course they have. An embedding is a relatively low-dimensional space into which you can translate high-dimensional vectors. I included extra context because that was very confusing to me. Embeddings make it easier to do machine learning in large inputs like sparse vectors representing words. Good. Ideally, an embedding captures some of the semantics of the input by placing semantically similar inputs together in the embedding space. So I think they actually defined embedding as embedding space, but either way, the whole thing's confusing. IBM. Embedding is a means of representing objects like text, images, and audio as points in a continuous vector space where the locations of those points in space are semantically meaningful. So that's probably the best of the ones here, I would say. I've still got a few little issues with it, but we'll get to those. But I'm going to give my own definition of embedding that is a little bit more abstracted than these. An embedding is a coordinate in a vector space into which we map a concept. And why I'm being so careful and precise here, if you think about where the phrase embedding came from, it's not my favorite word. Again, thought vector, something like that I prefer. But the idea of an embedding is that you actually are taking a concept and you're taking a vector space and you're sticking that concept in the vector space somewhere. And so this is easy to visualize with images, right? If you go to like the gnomic example here, where you can search for Darth Vader, and then these particular images are at these coordinates in this vector space. The vector space has been defined, and you're saying, here's my vector, and the vector is the set of coordinates that get you to the place in vector space that represents the concept you're talking about. And so I'm going to go with this definition for this talk, and I think it also opens up room for some other things that we'll talk about later, but it's a coordinate in a vector space. I didn't say in a numerical continuous float vector space. I just said it's a coordinate in a vector space into which we map a concept. All right, so we'll continue on. So these are all just different things you find in a vector space. Some puppies here. Always makes talks better when you have cute puppies. All right, so taking that a step further, I would argue that an inverted index creates embeddings which have one dimension per term. So if you think of, hey, if every single keyword or term in my index is a feature, is a dimension, maybe there's millions of them, and if it exists, there's a 1, and if it doesn't, it's a 0, I would call that an embedding. It's not a semantically meaningful embedding beyond that individual word, because the coordinate I'm giving is still in a vector space, right? It's really in the same vector space that we would map, any kind of language into and concept into. It's just that it's represented by millions of features, each of which have a single term, versus being condensed down into 1,024 or 512 or what have you features. Embeddings map concepts into another vector space, usually a lower dimensional space. So I can take all the words in my inverted index, all the words in my corpus. I can then map them down into 1,024 dimensions, and those can be latent features in some embedding model. I would also argue that you could take features and you could expand them to more dimensions. You don't have to always do dimensionality reduction. The value of dimensionality reduction is that we can go from a higher level, like a bunch of keywords, for example, and when we compress them down into lower dimensions, we unveil some connections, some semantically meaningful connections between the items that were previously at a higher dimensionality. But I would argue we could also extend the dimensionality. We do this if you think of sparse vector search. If you think of things like splayed, what do? We take a word, we find other things, and we expand out, and the features we're searching for, we're actually expanding because we can. You could argue it's the same vector space maybe, but either way, the embedding got expanded and represents more meaning now. And of course, we take these embeddings, we leverage them in the vector space to explore similarity. So if I've got these embeddings over here on the left for apple juice, cappuccino, a bunch of food items, I do my cosine similarity dot product, Euclidean does whatever distance. I then am exploring the relationships based upon those shared features between things. This is the basis for all the dense vector search and all the LLM capabilities we're exploring these days. But with LLMs and other foundation models, the dimensions learned are latent features. So on the last slide, when I was showing, cappuccino and showing a bunch of terms, I manually defined some categories that were the features. And so they were just, they weren't latent, they were just things I defined. But when we use neural networks to train transformers and embedding models, we, at that point, are, what all the features represent is not like one thing, right? It's a combination of all the features together, and those combinations basically unveil latent features that describe the documents. And we're going to return to this later, because I'm going to get off of embeddings for a second. But this is going to be really important when we start to think about how we handle signals and use those in a sort of vectorized embedding sort of way. So this is a slide I have in basically every presentation I ever give. It's the dimensions of user intent. And the point of this slide is that our job as information retrieval specialists is to help users find what they're looking for. Might be a document, might be an answer, might be an action, might be a task of going and doing something. But either way, the user wants something, and our job is to help them find it. In order to do that, we need to understand three contexts, as best as possible. One of them is the content that we have that we're searching over. Another is the user. What is their context? What do they care about? And the third is the domain. The user might say a word that doesn't have any meaning in the domain, but the user thinks it means something, so we need to understand the user there. There's domain-specific terminology we need to understand, and then there's the content that we actually have. And so if you take just content understanding, you're talking about something like keyword search. If you take just domain understanding, you're talking about a knowledge graph. Now that can be an LLM, that could be an explicit knowledge graph, a semantic knowledge graph, but the idea is it's something that understands your domain, the terminology, and what how the concepts relate. And then of course, if it's pure user understanding, I don't have any content, I don't know anything about the domain, I'm just looking at user behavior and trying to match and rank based upon that. That's like collaborative filtering, that's collaborative recommendations, purely based upon behavior. When you look at the intersections between these things, the intersection between content understanding and user understanding is personalized search, which we'll talk about today. Intersection between keyword search and knowledge graphs is semantic search. And then, I'm not going to get into the other one because it's boring, but user intent is the intersection of all of these. And so what we're going to talk about today is that personalized search part, the intersection at the very top. All of these topics are interesting. There's I've given lots of presentations. There's coverage of all of it in the book, but today is about personalized search. So the personalization spectrum spans, I used to call this the information retrieval spectrum, but it's too generalized. So the personalization spectrum goes everywhere from traditional keyword search all the way to traditional or collaborative recommendations. At a lot of organizations, you've got your search team, and they focus on user input and keywords, and you've got your recommendations team, and they focus on matching based upon user profiles. But it's all the same thing. At the end of the day, we're taking context, and we're using that context to match content or documents or what have you. So in the context of traditional keyword search, the context we have to do matching is what the user types in. They type in some keywords, they specify some filters, that is our only context. For traditional recommendations, our only context is information about the user, their profile, but we're not taking anything from them explicitly. But of course, there's this massive area in between for personalized queries, which are mostly specified by the user. They're typing things in, but we use what we know about the user to augment what we show them. And of course, user-guided recommendations, where you're given recommendations, but you can say, oh, actually, don't use this item to influence my recommendations. And can you filter my recommendations by this category? They're both search and recommendations. It's sort of a hybrid model, but the point is user context is part of the intent that we need to understand when we're matching for search. If we dig a little bit deeper into that spectrum, I basically just took the last two slides and overlaid them on top of each other. We've got the intersection of keyword search and user-driven behavior collaborative recommendations, and in between we have those personalized queries and user-guided recommendations. And I'll talk about recommendations first, and then we'll come back to the personalized queries. So recommendation approaches, you guys are probably all familiar with recommendations. I'm not going to go in detail, but we've got content-based matching, which we often do in search engines, right? Here's some information I know about the user. Let me match, whatever. This user typed detergent, and I know that fabric softener and detergent and dryer sheets are all related because they have similar, terms or categories or clustering or what have you. So you can do recommendations based purely on content. You can do behavior-based or collaborative recommendations using collaborative filtering algorithms, which we'll talk about today. And then you can, of course, do hybrid matching, hybrid recommendations using both content-based filtering and collaborative filtering and combining them together. Most recommendation systems do this because it works way better than one or the other. It helps you overcome the cold start problem, and it leverages your user behavior as best as possible. But another sort of audience question section. So for collaborative filtering, I want you to look at this for a second. So collaborative filtering doesn't know anything about your content. It's got documents basically, and that's it. But I want you guys to look at just the titles here, knowing what these documents are. I want you to tell me what's similar about these users. So anyone can raise their hand. Yep.
I was just going to say movies, movie characters.
They're all movies? Okay. Yep. They're all owned by Disney. The Dark Knight and the Batman are not. Yeah, but most of them are. Maybe some of the users are similar and others are. Maybe there's clusters of them. Like, do you guys see any obvious clusters amongst users?
Yeah, well, we've got the superhero users on the left, and then we've got the classic Disney movies on the right.
What's classic Disney?
The kids, the
Cartoons?
The cartoons.
Okay.
The kids.
Okay, so the user 4 and 5 like Disney cartoons, it looks like. Users 1, 2, and 3 like superheroes. 3 like some non-Disney superheroes. Everybody else likes Disney superheroes. But yeah, you guys, you can look at this, and even if you didn't know the titles of the movies, you know that the people who would watch these, even if you just had IDs here, these clusters would be found even with no content, right? So yeah, that's how collaborative filtering works, sort of intuitively. We're not going to go through code here, but this is an implementation of one collaborative filtering algorithm called ALS, or alternating least squares. It basically, well, I'll get into how it works shortly, but when you run this for a user, so I've got this user here. This is somebody who previously ran 2 searches, one for Apple and one for MacBook. And then they clicked on the Apple iPad 2, they added that to their shopping cart, they purchased it, and then they also clicked on an Apple MacBook Air. So that is the context we have about that user. Based upon that context and just doing collaborative filtering, if we take those results, we get the IDs of the things they've interacted with, or we do collaborative filtering and then we sort of boost documents in our search engine that are related to the things they've interacted with, then we get something like this on the right, where it's a bunch of Apple and tablet boosted type of things. This is being done as a search query in my search engine. So this can augment a user search. If they type something, you can boost things up that are similar to what they've done before. This is one way of doing personalization of search results. Very common way. And so, like, just as an example, if I just run a search for tablet in this naive, out-of-the-box, Lucene-based search engine, it's doing BM25 on my keyword of tablet, these are the results I get. How do you guys feel about those results? The BM25 score is great. They're not good, right? They don't have domain context. They don't have user context. When I add in the boosting based upon the items the users interacted with before and the recommendations for those, then the results get much better. So that's one way of doing personalized search. Another way of doing personalized search is using embeddings. So if we go back to this notion of an embedding having latent features. So these are features associated with these items at the top. So you've got 2 tablets of different colors. Looks like 2 washing machines, maybe a phone and a screen cover for a phone. And so there's a whole bunch of features in the vector. These are latent features, meaning they don't represent any one particular thing, but the combination of them does, and some numbers being higher are leaning towards certain items. So for example, this top one seems like it has something to do with size, or at least it's implicated in size, because the bigger these things are, the bigger this number seems to be. Color is implicated here. The darker it is, it looks like it's got a higher score. The lighter it is, it looks like it has a lower score. This embedding kind of means something like it's computer-like. It's some concept of technology-ish, computer-ish. The last one seems to have something to do with the price. Again, they're not explicit features, but they're latent features. This can be extracted from content. Going back to ALS and to our collaborative recommendations, the way that ALS actually works is that you create a user item interaction matrix. So you basically take all the users, you take all the items they've interacted with. The white squares here are items they haven't interacted with. So it's just, we don't know if they would like this or not. For ALS, when you implement it, it uses matrix factorization, which essentially tries to take that user item interaction matrix and convert it into 2 other matrices. One is a user feature matrix, and the other is an item feature matrix. Normally, when we're implementing collaborative filtering, we generate that, and then we use that and we multiply it back to generate something that approximates the original matrix. And that's how we do our recommendations. So that's how we recommend things the user's never seen before. But this intermediate form here is very interesting in the context of personalization, because what we've just done is we've generated latent features that describe users and latent features that describe items. Just like our embeddings coming from content that have latent features that describe content, we now have more latent features that describe content, but these features didn't come from the content that describes items. These features came from interactions with the items, meaning in addition to the embeddings that we can learn from just analyzing the entire web and building a giant large language model, we can also analyze our users' information to probably find very highly overlapping latent features, but also maybe discover latent features that don't exist in the content that the LLMs were trained from, even if it's our own data that fine-tuned the LLMs, because the users have insight that isn't necessarily in the data. So these latent features we can take and use as embeddings and use them to help match content. So we'll come back to that in a bit, but learned embeddings of users allow us to personalize results, whether it's just from their actions and we use those to map to vectors that are content-based, or whether we derive the embeddings from the user's behaviors. And so these are two examples of personalized search, and I'll show you the code for these momentarily. The one on the left has no personalization guardrails, and I need to define what that means, but think of it as when I'm doing personalization, this user has previously searched for and maybe clicked on a Hello Kitty plush toy. They've searched for a GE electric razor that's in black. They've searched for a GE bright white light bulb, and they've searched for a Samsung stainless steel refrigerator. All of those things are things the user has interacted with. Naively, if we try to implement some sort of personalization based upon those items, you're going to get something like this on the left. So they search for microwave. You're going to get a black microwave because they search for a black razor. You're going to get a Hello Kitty microwave because apparently that exists. And they apparently like Hello Kitty. And you're going to get this white microwave from GE because they search for a GE electric razor and GE white light bulbs. So even though which of these items is the most relevant for what they're looking for right now, would you say, out of these four? Up here. Samsung stainless steel refrigerator. All of you knew that that was the most relevant. How do you know that? It's an appliance, right? That you've got the context that, oh, this is an appliance. I should probably look at their preferences within the context of appliance. So let's implement that and get what we have here on the right instead. So one way of doing that is we can take all of our items. We might have category labels already assigned to them. I actually do in this data set, but let's throw that out. We're just going to cluster all of our items so that we can generate dynamic categories for the items. Also categories that have similarities and are close to each other in a vector space so that we're not creating hard delineations. So I'm not going to go through the code. You guys can look at the code afterwards. But this is code to cluster products based upon embeddings. So to be specific, these are embeddings generated from the content of the product. So this is titles, descriptions, that kind of thing. Based upon that, we map all of our products into a vector space, and then we cluster based upon those to generate these clusters here. So we've got many more dimensions than this, but if we do dimensionality reduction down to 2 dimensions here, you can see that all of my products sort of fall into this space, and it might be you guys in here can see it on Zoom. Hopefully you can as well. But what you see is that up at the top right here, you have things that are CDs, mostly music, CDs having to do with music. Over here on the left, I've got ranges, microwaves, stainless steel, range, self-cleaning. So this seems to be appliances over here. Down at the bottom right, I've got widescreen DVD, widescreen. This seems to be video sort of content. So audio's at the top, video's down here. So whatever this dimension is, soundish things and video-ish things down here. Appliance-ish things versus, CDs and digital media-ish things over here. You see like computer, memory, these kinds of things down here. But you get the idea. We've taken all of our products and we've clustered them, and these are the clusters, the centers of the clusters, and I've given them all labels. Now that I have that, we've got all our products mapped into clusters. Why don't I map my queries into clusters as well? So the user comes in, and again, we're going to use the same search. They're searching for microwave. So, and again, the code's here. I'm not going to go through the code. You guys can look at that later, but I'm just going to talk about the ideas. What we're essentially doing is taking the query and mapping it into the clusters that we've generated for the content to generate these contexts under which we personalize. And there's kind of 3 different ways of doing that. There's more, but 3 obvious ways of doing that. One is we do a k-means on, hey, we've got our clusters. Let's find whichever cluster is going to be the closest based upon our space. Another way is to do a cosine predicted cluster. So, hey, I've got a vector for my query. I've got a vector for all my documents. Let me do a cosine and find the clusters that are the most that are the closest. Then the last one, which is what I recommend, is we use the cosine, but we get multiple clusters. So I don't want to, if I've got a category, you may have seen it on the last slide where I've got, here's my ranges, and here's my stoves, and here's my refrigerators, and here's my freezers. They're all appliances. They're all kind of similar. So you don't want to hard cut somebody off to be in just one of the things that where the product happened to get clustered. So instead, if we say, hey, just find me the 5 closest clusters, and I'm going to use that context to limit my personalization. So that's what we're doing here. So I'm finding the 5 closest clusters within our products to microwave. And so you see here it's microwave, stainless steel oven, stainless steel black KitchenAid, 30-inch range stainless steel, range, refrigerator, all appliances. And just for reference, these labels just came from finding the top keywords in each cluster. So that's where the labels came from, just so you know kind of what you're looking at. And then we're going to use those. So once we have those, we've got a couple of different approaches we can use to take those contexts and the user's query and map them into an embedding-based personalization using an embedding for the user. One is we could perform a weight, and sorry, this is a lot of text, so just you can look at the yellow or just listen. We perform a weighted average between the query vector, so the embedding for microwave, and the vectors for the user's previous interactions with the predicted cluster. So that would generate a single vector representing a personalized version of the user's query. So all the results would be personalized. We may or may not want to do that. Another way is to perform a standard search, but then keyword or vector or hybrid or what have you, and then boost the results based on the average of the embeddings from a user's previous interactions with the predicted cluster. That would be a hybrid keyword and vector based ranking function where the keyword search would be the primary driver of the results, but the user's previous interactions would be used to boost related results higher. Third option, do either one of the above, but then only personalize a few items in the search results. So instead of my 10 results being all personalized, I might say, hey, let me maybe leave result 1 and 2 and boost, maybe let's sprinkle some personalization in case we're wrong or in case the user doesn't like personalization, so most of the results look good. This is often a good approach. It's a very conservative approach and not a bad one for many use cases. And then the last option here is to perform a standard search, again, keyword or vector or hybrid, and then re-rank the results based on the weighted average between the query vector and the vectors for the user's previous interactions with the predicted clusters. So you saw that I got multiple clusters coming back. Some of them maybe weight higher than others, but if I sort of take a weighted average between the query vector and the vectors for the user's previous interactions, then I can use that as my personalization vector for the user. So again, I don't want to spend time on code because we'll do hopefully questions and stuff at the end. But this is code to generate a personalization vector for the user. See if there's anything here. Get personalization vector. We're calling encode on a transformer. Create embeddings. Wait. Taking average. So it's just a vector that combines the weighted average embedding for the query. Yeah, I'm going to keep moving on for this one. We'll look at the code later. Once we've done that, we can generate contextual embeddings, contextual user personalization vectors. So on the left here, I'm taking, these are the items that the users interacted with before. So this top item is a Hello Kitty water bottle, and this next one is a stainless steel electric range for reference. And we're getting the user embedding, taking the query microwave. This unfiltered personalization vector is getting a vector that just uses all of those embeddings to boost the search results. This filtered one is getting the context of what clusters have been interacted with before. So over here on the right, you can see these are the product interactions for the user, these 2 items, the Hello Kitty water bottle and the stainless steel electric range, with no cluster guardrails, no context being added. This is my average vector of their past interactions. If I use that to boost the results, you'll see the Hello Kitty microwave show up, that example from earlier. But if I find the clusters that they've interacted with, I find the cluster for the query, and then I filter the past behaviors that I'm going to use for personalization based upon the clusters that are related to the query. Now I'm taking, maybe the user has interacted with 100 things, but I'm going to filter it down to only the 5 things that are in this category or cluster of categories. And then I'm only personalizing, in this case, for appliances. And so now I'm basically only using that one embedding, I'm only using that one item because the other ones got filtered out because they're not related to appliances. And so this ends up being my personalization vector for the user with the guardrails. This code's boring. This just runs different scenarios. The first one is just a basic search with no personalization. The second one is, the second one is doing global personalization, and then the third one it generates is contextual personalization with the clusters. This is what the results look like. So this is just a search for microwave. I see a white microwave, a stainless steel microwave, a microwave popper for popcorn, and then the Hello Kitty microwave down here. So that's no personalization. That's what you would get out of the box. With global personalization, that beautiful Hello Kitty microwave is here, and a bunch of other random microwaves. And then with my contextual personalization for only considering categories that are related to what the user is currently searching for, I get a bunch of stainless steel microwaves, way better than the other approaches. Last thing I want to kind of mention here is we're talking about the latent features that you can derive from user signals by doing matrix factorization. And we think about multimodal models often. Oh yeah, text to video, text and image to video, like all of these different modalities. The reality is, we've got text, we've got images, but user behavior is one modality that I think is highly unexplored currently within our space. The reasons are pretty obvious. Hey, we had keyword search, then we had vector search. These LLMs are amazing. We get these embeddings for free. Other people pay millions or tens of millions of dollars to train them for us, and it just kind of is magic. We just put the embeddings in there, and it's all just magic, right? But we're ignoring our user context. We're ignoring our data that can tell us more information. So it's definitely possible to do joint encoding embedding models to sort of factor in these additional features that come from user behavior. I would highly recommend, I think, that we explore those areas. Also, my general context in the book, the context as well, is that there's many different query modalities. So there's a lot of talk here about hybrid search, right? And I think when people say hybrid search, usually what they mean is lexical and dense vector. I'm not going to call it semantic, because semantic means a lot. But they mean, let's combine these two different things together. My view is it's not two things. My view is there's a lot of things, right? There's, what do you do in a traditional query pipeline? Well, you parse the query. Of course, you get keywords, locations, things like that. You do a signals boosting model to try to make sure that your most popular results get boosted to the top, a popularized relevance algorithm. You do, sort of knowledge graph lookups. Now, this can be LLM based, or this can be semantic knowledge graph, or what have you, but you look up things that are related to your query to add some structure and understanding to it. You, maybe do lexical search on inverted index, filtering on categories. You do, sparse vector expansion with things like splayed or semantic knowledge graphs. Maybe apply geo filters, things like that you don't get with the dense. Certain models have certain capabilities, but these are all different modalities for hybrid, right? These are all hybrid type queries that you put together. Additionally, the dense vector stuff with cosine similar to dot product or Hamming distance or what have you. We've got backfilling. You might do personalization, recommendations, but all of those things together in a pipeline, or maybe multiple pipelines depending on the context, are ways of doing information retrieval. They're ways of matching and ranking. And to me, hybrid means take all of these different techniques, take signals boosting, collaborative filtering, learning to rank, dense vector, sparse vector, query expansion, sparse query expansion, take click model, take all of it and use the appropriate tool where you need it. So it's to me, it's not hybrid, keyword lexical versus dense. It's hey, there's a lot of techniques we use here in AI-powered search, and we need to combine them all together. Last thing on just signals. So this idea of reflective intelligence or feedback loops is really important in AI-powered search. So we talked about collaborative filtering and taking user behavior, building models. We feed that back into the system, so the personalization is constantly getting better, the recommendations are constantly getting better. But there's lots of different AI-powered search algorithms that we use for things like this. So, whether it's signals boosting, feedback loops, collaborative filtering based reflected intelligence, learning to rank based, where you're getting implicit judgments from user signals and click models, or these sort of personalization profiles like we looked at today. I would just encourage you guys to, think about these things and try to get them implemented where they make sense within your products and customers. So that's it for me. AI-powered search is the book. Check it out. Talk with me if you're interested in, integrating or helping to promote it. And I don't know if I've got any time for questions. One or two? Okay. Thanks, guys.
Thank you, Trey. We have time for a question or two. I see a hand.
Yeah, you're welcome. No, thank you. I know some of the text looked like it was plagiarized on a book that I read called AI-Powered Search.
Don't tell the author.
Yeah. But you're basic, and summed up that we should be doing all of these things. Do you have guidance on how to combine these? That's
enough.
Yeah.
Real questions, please. Real questions.
Thank you for the great talk. You mentioned personalization and user interactions. To me, that's something we can do with historical data, but also with first-time visitors. What do you think about real-time personalization of anonymous visitors?
Sure. I've got it. So real-time personalization of anonymous visitors. So I think of search as taking context and using it to match and rank. So whether that's keywords, whether that's what you know about the user. So say someone comes to let's say it's a job search website. Someone comes to it for the first time. What context do you have about them? You know their location from their IP address, right? So if they come to your homepage and you're showing some jobs, should you show them jobs in Japan and London and South Africa? No, you should show them jobs where they're located. That is personalization. That is first time, all the context I have about you is your location, and so I'm going to use it. If someone likewise comes to the site and they type in Atlanta, Georgia, but you know that they're a registered nurse, should you be showing them software engineering jobs and brain surgeon jobs? No, you might show them the same set of results, but you're going to boost results that are more likely to be relevant for them at the top. Those are light ways of doing personalization that almost always make sense and don't frustrate users. As you continue to get more interactions, you get more context. Obviously, you have to be careful, like we did with the guardrails, and make sure you're not over applying personalization, because you can really frustrate people if you personalize something they're not expecting it. You have to apply it with a light touch. But yeah, absolutely, you should use whatever context you have. You should take whatever context you have, use whatever means you have to figure out if you should use that context in your query, and then use it if it makes sense. Yeah.
All right, we have time for just one more from the Zoom. Alexandra asks, how do you measure personalization?
How do you measure personalization? I assume you mean so I'm going to assume that he means in terms of precision, recall, the typical IR metrics. Okay, so I'll go with it. At the end of the day, our job is to give the user what they're looking for to meet their intent. We have metrics for standard keyword search where we've had people create judgments and we measure those. It's very hard to do that with personalization because every result set changes for every user. So what you typically would do is tie it to a business metric. So if it's product search, you tie it to, hey, are we selling more? You maybe look at drop-off rate, things like that. You could also just see about user satisfaction. But I think that it is harder to measure because you can't have a standard training set that you use to measure it based upon. So you have to look at, I think, some other metrics that are about overall business success and overall success of the engine at helping the user meet their need versus just something more static.
Thank you, Trey. And let's thank our speaker.
All right, thanks everybody. Appreciate it.
We have 12 minutes until the next talk.